Good afternoon and welcome to the webinar of the FTTH Council Europe on 5G and FTTH, estimating the value of convergence. I am Ajibet Fitori, the Director General of the FTTH Council Europe, and I will take you through some of the kind of practicalities of this webinar and say a few words about the FTTH Council Europe. Then I will hand over to Raf Meersman, who will be presenting the key findings of the study. The webinar will consist of a presentation approximately 40 minutes long, and then we will be responding to the questions for about 15 to 20 minutes. If you do have a question at any time during the presentation, please do write your questions in the question box of the webinar system, the questions that are most asked and we have time for, I will be reading out and Raf will be responding to them during the webinar. Some relevant questions for which we might not have time will be answered by email after the webinar. The webinar will be recorded and it can be viewed as a video stream after the actual webinar, and it will be available, the link will be available on our website. And everyone who has registered as an attendee for this webinar will receive both the slides as well as the information with the video link. We would very much welcome you to follow the activities of the FTTH Council Europe. For those attendees who might not be familiar with us, we are a non-for-profit organization representing the interests of approximately 150 member companies, predominantly technology innovators, fiber network operators, as well as investors in the fiber space. We work towards a very clear mission, which is to accelerate the availability and take-up of full fiber-based connectivity across Europe. We would welcome you following us on social media links. And if you do have any comments on the webinar, please do post them on Twitter with the hashtag FTTH webinar. And I would just like to introduce a little bit the project that will be presented. It will be presented by Raf Meersman, who is the project manager of this study on behalf of the FTTH Council Europe's Deployment and Operations Committee. He's also the CEO of Comsof. By way of background, the FTTH Council Europe is part of a global alliance. We have sister councils across the world, and the first joint project of these global FTTH councils was a white paper on explaining 5G. And that was led by our American sister council, the Fiber Broadband Association. We took over the chairmanship of the Global Alliance in 2018 from the Fiber Broadband Association, and the joint project under our chairmanship was this quite novel approach and aiming at quantifying the value of network convergence between FTTH and 5G. And with that, I will hand over to Raf, who has led the project, to hold his presentation.
Yes, thank you very much, Ajibet, for your kind introduction. And also from my side, welcome everybody to this webinar. I indeed want to take you through a lot of background info on how we achieved the results in our study. We previously already communicated the numbers at the FTTH conference in Amsterdam. And basically what we said as an outcome of the study was that between 65 and 96% as a range, the fiber costs for a 5G backhaul or front haul network could actually be avoided or eliminated if you roll out an optimized and future-proof converged fiber network. The range coming from the fact that we evaluated a large number of different scenarios and obviously looking for how to save on costs if you do an optimized converged network deployment. And on the other hand, we saw that the extra investment on top of a full FTTH network to make that network also ready for this 5G extension, even for a high cell density, was only in a range of 1 to 7%. Both results being, I would say, on the even more promising than we expected upfront. Here you see the overall summary of the major results. We did calculations for 3 different types of areas, ranging from high to low density. And we also considered in every area 3 scenarios for cell density. I'll walk through the assumptions behind these, but here you see the major outputs, and we reflected always 2 percentages. The first percentage is for each scenario. How much of that fiber for 5G that could be eliminated in a converged deployment. And the other one is the extra investment on top of FTTH to make your network 5G ready. Now, some of the things you see in these results, obviously, when we talk about a low cell density scenario, it means we're considering that 5G will be deployed on a number of sites, but not really being ambitious on the real densification of those cells. In those scenarios, it's clear that still a lot of the costs obviously can be eliminated, and the extra cost is very small on top of FTTH because we're not really talking about a very high dense 5G network. That's why also I personally believe the medium and high cell density are true long-term future-proof 5G networks and are probably the most interesting scenarios to look at when we look at these numbers. And another interesting finding in general is when you compare the numbers across the different densities of areas, is that the impact of this density is not enormous. There is an impact, but certainly not a very big one, which also means that these convergence opportunities certainly exist across all these types of areas. Now, to explain how we get these numbers, let me first take a look at this high dense area, high cell density, where we report a 74% saving for FTTH-5G and a 5.6% extra investment. To understand where these numbers come from, we actually calculate 3 scenarios on this high dense area and high cell density scenario. The first calculation that we do is a full optimized cost of a fiber to the home network in this area. In this case, we calculated an estimated deployment cost of 8.5 million euro. The second calculation on the same area is a pure optimized fiber to 5G network. In this case, we just fiberize all the cells and we calculate the cost of this fiber network. In this scenario, we come with an estimation of 1.85 million euro as the cost for this fiber for 5G network. And then the last calculation on this same area is a fully converged network that will consider both the residential endpoints and the 5G cell sites and plan an optimized converged network. And this network is estimated to cost around 9 million euro in this scenario. And it's from these 3 numbers that we estimate or derive the different percentages that we reported. So we have saved, if you compare the orange with the stack of the 2 costs, we have saved 1.37 million euro versus the original cost of 1.85. So you see we eliminate 74% of this blue bar for 5G. And on the other hand, we calculate almost 500,000 extra investment on top of the 8.5, resulting in our 5.6% extra investment needed. So this is how we calculate these 2 percentages across these 9 scenarios. Obviously, furthermore, for calculating each of these scenarios in each of these cases, we need to put in a lot of other assumptions, parameters, and also use different models. So in the remainder of this presentation, I will take you through all these major assumptions. And for sure, we know that currently we did already a nice set of scenarios, but we certainly don't think that we cover all the possibilities. Every case is different and there's probably a million combinations. But at least what we try to do is to come up with realistic scenarios and thus also realistic numbers, and want to offer full clarity on the assumptions behind these scenarios. So when we look at our calculation methodology, there are actually two important models that form the basis of these results. First of all, there is a 5G propagation model that is used to really have an accurate view on cell density in 5G. We thought it was really needed, and it's really not done yet in a lot of studies, but we really wanted to see what a realistic future-proof 5G network could look like in these different areas. And therefore, we really looked into all the different aspects of these 5G technology and what it means in terms of density of cells to reach a certain coverage. And then on the second hand, we need to calculate the costs of the fiber network, for which we use the FTTX design and calculation model. For the 5G propagation model, the major inputs are, on the one hand, a 3D area data. So we actually use a full 3D view of an area. So because it's very important also to know where obstacles are, in order to know how a signal, especially at higher frequencies in 5G, would react and would propagate, and as such would also determine the coverage that we could achieve. In our model, we also start from a large set of candidate sites where a 5G small cell, for example, could be deployed in order to let the model choose the best set of candidates for a 5G network. And then there's obviously a large set of 5G technical parameters and also the real frequency at which we operate, as well as a target coverage, focusing mainly on the coverage outdoor. From this calculation, we will get a selected set of sites that will fulfill this target coverage given the area and all the other technical assumptions. So that is the first point, set of sites where we want to bring fiber to. But obviously, as you saw, we also want to do the FTTH calculations. So we also need to add information about, for example, address points and more precisely residential homes, because those will be the endpoints of the fiber to the home and thus also from the fiber to the all network. And we also need 2D area data, including streets and building information in order to do these calculations. And then ultimately as input, we need FTTX parameters, where we talk about choices for the FTTX architecture, materials, type of materials that we want to use, and the unit costs of all the components that are involved in such a network deployment. And as ultimate output of that, we get those three calculations, one for fiber to the home, one for fiber to 5G, and one for the converged complete network, from which we can then derive our percentages. So now we'll go step by step through this model and inputs to see what are the different data and assumptions that we took for this study. So let's start with the 3D area and candidate sites. 3D data, more precisely 3D LiDAR data, is a crucial input if you really want to model the propagation of the wireless signals. And more of this kind of data is becoming available. So in our study, the three areas that we ultimately chose for high to low density were areas where we could actually use such data so that we could do these propagation calculations. For the candidate sites, in our areas, we actually also had the lampposts and considered the lamppost as possible candidates for small cell deployments. This is again just one assumption, but it at least gives us a concrete set of candidates across the whole area where we could install a small cell with 5G technology. If you look then, for example, here to our high dense area, this is how this data looks like. On the left hand, the 3D digital map data, where you see even, well, the height of buildings is crucial, obviously, but also, for example, trees or parks and vegetation can play a role in this propagation model. And on the right side, you see a concrete set of almost 1,000 points with the lampposts that are serving this area. The next step is to determine the 5G parameters. Here, obviously, a lot of options and choices can be made, certainly because 5G is a technology that supports a lot of scenarios, not at the least from a frequency perspective. So we had to make some choices, and there are many other choices that could be made, but the choices that we made were to look at 5G as a heterogeneous 5G network, where we would actually start in a first phase to deploy 5G from current macro sites, typically 4G macro sites, and they are typically also on dominant rooftops within the area. And from those macro cells, deploy a 5G network, calculate the coverage, and then see if there are areas that are underserved. And in those areas, we would then look for interesting small cells that could be deployed in order to fill the gaps and to increase the coverage. Specifically in high dense areas, we actually also considered some indoor hotspots in very public big places like train stations, university campuses, or cultural centra. From a frequency perspective, we took the choice to start looking at a 3.5 gigahertz 5G spectrum deployed from macro sites and small cells at the first instance. Clearly, this is an upgrade from 4G, but not to the full extent of what 5G could be. The typical sub 6 gigahertz spectrum in that perspective is still one where there's a lot of interest and a lot of frequencies occupied, so there's not a lot of bandwidth available. And on the other hand, it also, from that point of view, doesn't necessarily allow very high speed applications. That's why in more future-proof or more ambitious plans, we also added an extra layer of 26 gigahertz coverage deployed from small cells, and typically also using two sectors to go in two opposite directions from our small cell. In the model, we also consider beamforming because that's an important aspect within 5G to extend the coverage. And we then work with several scenarios for a target outdoor coverage, along with a minimum data rate that we want to obtain in that outdoor area. Optionally, also, we can look at indoor coverage. Important to note is that when we talk about the high to low dense areas, and the meaning in low dense, we are talking really about a rural area, that there we actually do not consider small cells with the 26 gigahertz as a viable, at least business-wise, scenario on the short term. That's also why within the low dense area, actually none of our scenarios considers 26 gigahertz, but rather sticks with the 3.5 gigahertz coverage scenario. Whereas in high and medium dense area, we do consider that 26 gigahertz as an additional part of a 5G network in this case. So what you see in this is per scenario again, you actually see which coverages at which frequencies we considered for these different cell density scenarios. And as I said, what's important to see is, for example, at 3.5 gigahertz, typically we would aim and relatively quickly achieve 100% coverage. So the cell densification for that is not necessarily an extreme cell densification, but it's really when starting to add small cells at 26 gigahertz that you see the effect of the higher frequency, which results in a lower coverage from the cell side, and thus also requires a lot more cells to be deployed. On a technical perspective, there's a lot of real technical details that go into the model. Here I need to say special thanks to Cyrodiil, our partner in this project on the wireless side, because from a fiber to the home council perspective, we are obviously all more fiber experts, whereas 5G is obviously a wireless technology. So the knowledge and experience from Cyrodiil here was vital to come up with realistic assumptions. Again, we're not saying this is the only truth for 5G, but it is a realistic set of assumptions on, for example, available bandwidth at a certain frequency, number of sectors that you can deploy from your side, numbers on the transmission and receiving power, signal to noise ratio that will be needed to still be able to deliver a certain speed. And what you see at the 3.5 gigahertz scenario is that actually we are with these parameters capable of offering a 15 to 30 megabit per second service. As you see, this is a nice speed, but it's not enormous in terms of bandwidth. Nevertheless, of course, 5G has other benefits, but we, in the 26 gigahertz spectrum, we clearly see that by deploying this, we can actually start offering and thinking about services in the hundreds of megabits per second through this wireless link. Obviously, for that, needing also a much higher number of cells, so a bigger cell densification, because we need more power that remains at the receiver side. Now, with all these inputs, both on a geographical area basis and on a 5G technical parameters, we can feed the model and let this model do its calculations. So we use the Cyrodiil Volcano model for the propagation of the data, also building on the 5G ready map data that Cyrodiil could provide for our test areas, and ultimately from that could calculate coverages for 5G mobile access, and based on this 3D city model. And thanks to this accurate input data and accurate technical inputs, we can see that we have a very good view on what the needs in terms of cell and cell densification for each scenario would look like. To illustrate this, let's look at the high dense area. And what you see at the beginning is the current macro sites, in this case 6, which cover this area. As we said, a first typical 5G step would be to deploy, for example, a 3.5 gigahertz network from these macro sites. Of course, at this stage, we are not really densifying, but thanks to the higher frequency, we actually have the drawback of having a smaller coverage. And to fill up the gaps in that coverage, we can install small cells at 3.5 gigahertz that will extend the coverage at this frequency across this area. Here you see in this picture how this propagation is actually calculated and reported to see that indeed with the combination of macro and small cells that we have enough power in 95 to 100% of the outdoor areas in this region. As we said, for a high dense area with a lot of visitors, there is also a typical scenario where indoor hotspots at this 26 gigahertz would be useful, especially because at high frequencies and with a lot of attendees or people being together in a room, the indoor penetration of a high frequency signal through walls could be an issue. So therefore, an indoor hotspot could be a good solution in a 5G network for such public places. Based on this example area, in this case, it makes sense to foresee 13 of such hotspots. This results in a first cell densification scenario, seen as the low cell densification scenario, where we actually go from 6 macro sites to 30 sites, combination of macro sites and small cells and indoor hotspots. And this is our first output as the high dense area, low dense cells, where we will do calculations on. But as we said, this is not necessarily an endpoint for 5G, and is also not for 5G readiness. If we look further into the 26 gigahertz outdoor coverage, and let's say our initial target would be to cover also 50% of the outdoor with the 26 gigahertz, the calculations show that we would need 40 small cells across the area to do this. Well, and if you look at it, the 11 that we had for 3.5 gigahertz, we could actually reuse, and we would have 29, the blue ones, that we would add to this area in order to have that 50% coverage. This is our definition or assumption of our medium cell densification scenario, and is a factor around 10. The most extreme case would actually come from targeting a 95% coverage at a 26 gigahertz, in this case needing a total of almost 120 sites across the whole area to reach this target. And this is our high cell densification scenario, which is for sure in the coming 3, 4, 5 years probably not even that realistic, except maybe in some showcases. But again, we want to be very future-proof, very forward-looking, because we believe the fiber networks are installed for a very long time. So we want also to make sure that we can use this fiber even in the long term. And it's talking to industry experts, it's clear that this migration path, where every time more cells can be introduced and densification step by step goes up, is certainly a realistic scenario. Whether this factor 20 is realistic is open for debate, but at least that is our most extreme scenario that we considered here. And again, in the slides here, you see the actual wireless analysis and reporting, which is showing the why with this amount of cells we can actually get this high coverage. So summarizing, we can say that we identified 3 cell density scenarios on this urban area, from low to high, where we gradually increase the number of sites. From 6 macro sites, we go first to 30, then to 60, and then to around 120, as 3 illustrations of cell densifications. Obviously, the high dense area is not necessarily the same. So what you see here is the scenarios that we calculated and used on the medium dense area. Now, medium dense area, there's also a lot of options there. Actually, we have a relatively high dense population, meaning a lot of houses close to each other. But a big difference in this case is that most of these houses are single dwelling units or villas, relatively close to each other, but not a lot of high-rise buildings. The scenarios that we considered in this area started from 7 macro sites, where we deploy a 3.5 gigahertz again, and then adding small cells first at 26 gigahertz for limited coverage, I think around 30, ending up with a factor 4 from 7 to almost 28 sites needed for that. Adding 29 extra cells to come up with a 50% coverage, which means a factor 8. And then for a 95% coverage at 26 gigahertz in this area, we would actually need almost 110 sites, which is around a factor 16. So you see the factors here are different because our assumptions are also different, given that this is also an area needing another type of network. And then obviously the rural case is completely different. There we actually go from 2 macro sites to adding 2 small cells in a first instance to increase at least the coverage in the towns, adding 4 more to extend that 3.5 gigahertz coverage a little bit more, I think up to 70 or 9, I think, no, it's 98% for the medium cell densification. And then in the high cell densification for 3.5, we can, on the outdoor level, reach 100%. And on top of that, we can increase the indoor coverage. The detailed numbers obviously were on the previous slide, so you can check them afterwards if you like. But as you see, this is a completely different scenario in terms of densification. And we are certainly not applying the same rules of densification to the rural area as what we would do for the high dense area. And to conclude this part, you see here the analysis again of the coverage in the village, so in the populated areas for the medium and high cell density, where we also look at the propagation and the coverage with the volcano model from Cyrodiil. So thanks to this model, now we have actually a list of selected realistic 5G sites for the 3 densification scenarios and for the 3 types of areas. As we said, for the FTTX model further, we needed 2D data, meaning streets and address points, that will be needed to estimate the costs of a fiber to the home network. And for the 3 areas, this data actually looks like this. So the high dense area, again, you see there's an extreme high density of inhabitants. And they are also scattered around 4,000 buildings with 30,000 families. So it also includes a lot of multi-dwelling units. If you look at the snapshot from the suburban area, density of population is much less, but still houses are very close to each other and spread across the whole area. This would be actually a bit of a typical example of an US-based residential environment. And then the final area, the rural one, is really where there's some isolated villages with a couple of hundreds of homes, and then a lot of empty land, like agricultural fields, for example, in between those villages. Then the final inputs that we need for the model are the FTTX parameters, referring to the architecture, the materials, and the unit costs to be used. On the architectural and material assumptions, for the fiber to the home scenario, we considered a point-to-multipoint GPON network with 1:32 splitters deployed in distribution points, so in the field. Let's say a decentralized split scenario. We foresee 2 fibers per home, 1 active and 1 spare. The spare running just until the distribution point. And these distribution points are actually installed in the form of cabinets per 60 to 96 homes. Depending on the density of the area, this parameter can vary. In the first calculations, we consider a full underground network with microducts and air-blown fiber. Later on, we also have scenarios where we would deploy the cables between poles, avoiding the ducts and the trenching. And then in the feeder network, between the central office and the distribution points or cabinets, we use the mid-span access cable of 96 to 48 fibers in bundles of 8 fibers, which we dropped per cabinet, which is an efficient way of deploying the fiber count to these different distribution points. So those are the architectural material choices for fiber to the home. For fiber to the 5G, the main question and parameter was actually the number of fibers per cell site. Ultimately, we played along with the parameters and considered 4 scenarios. We could do point-to-point fibers per site, or we could do point-to-multipoint, putting some of these fibers higher up in the network on a splitter. And we considered scenarios where we would do 12 active fibers plus 12 spares for the first part of the network deployed per cell, or 4 active plus 4 spare. You might question why not even 1 fiber could be enough, but actually when you talk about, again, the future-proofness of the network, and you look at the data rates that could be served in these scenarios, and at the same time, if you look at the scenario where you still need to deploy your fiber network anyhow, then we believe these are realistic numbers. Of course, if a fiber network is already deployed and you only have a couple of fibers left, then technologies like a WDM PON, for example, could help to squeeze more speed out of your fiber network. But in our calculations, we assume that we foresee enough fibers to start up without even a WDM PON and still have enough bandwidth to serve the backhauling of the 5G network. In the case of point-to-multipoint, we group typically per 4 antennas on an aggregation point where we install a 1-on-4 splitter in order to combine the traffic from the 4 antennas towards the central office. And then ultimately in the converged network, we combine kind of these 2 types of networks. And the interesting case is where our antennas are actually grouped on an aggregation point with the splitter. We can actually reuse also the cabinets and the distribution ducts of the fiber to the home network if we take that assumption in the converged scenario. Another very important input for these calculations of the FTTX network are the unit costs. Again, here there's a lot of variety and options possible, not in the least already from the country perspective. Typical big costs like trenching could be influenced enormously by the labor costs in the country, or also by the type of surface. For example, if it's a lot of rock and mountains, will be much higher than if it's, for example, more sand as a basis. These numbers that we use today are just, again, one assumption, which could apply to some countries, but not to all of them. And the numbers are for urban areas on average an 80 euro per meter cost, street crossings at 1,200, suburban 50 euro, street crossings at 640, and rural 35 euro per meter, and street crossings at 400 euro. And then there's also a couple of materials like ducts, between 3 and 4 euro per meter, cables between 1 and 3 euro per meter, and cabinets between 3,000 and 4,000 euro per cabinet. These numbers, again, relate mostly to what was used previously in the EU cost model some years ago, and which were at that time the result of a questionnaire that was sent out to the members of the FTTH Council, as such representing in our case some European averages. Might certainly not necessarily apply to other continents, but even within Europe, we see a lot of difference on a country-by-country basis. So again, these numbers need to be treated with carefully. Also important to consider or to remember is that there are a number of costs not considered in our calculations. For example, all the fiber termination costs on the private domain for fiber to the home, entering into the home, installing, terminating the fiber, all of these costs are not in our numbers. Same with active equipment for fiber to the home, both in the home and on the central office side. And also 5G active equipment, 5G site acquisition and connection costs, and 5G spectrum costs are totally not considered at this stage. This means all the costs that we are reporting are mainly costs of the outside planned passive fiber network. And that is also where, of course, the convergence and the opportunities lie. but it means also our numbers are certainly also not the full business case numbers, because there are other costs that would need to be considered for that study, but that is out of scope for this model. So considering all these inputs again, feeding them into the FTTX model, we can calculate our designs and costs. So for this, we use the Comsof Fiber software, which allows, on the one hand, to calculate the individual FTTX scenarios, so both FTTH and FTTIA from antenna. It also supports the hybrid design, so you can combine the GPON with point-to-point Ethernet connections. You can combine fiber to the home with fiber to 5G. We have rules that would be working well on high density areas, and other rules that would be optimizing the situation for low dense areas. And the calculations ultimately are cost optimized and also realistic. What you feed into it again is the GIS data and the rule configuration. What you get out of it is an accurate and realistic FTTX network design that shows on the map where the cables are routed, where the cabinets are installed, and also summarizes all of the materials and the costs for that network, so that these costs can then be used for our analysis. So that brings me to the last part of this model, which is the ultimate results of these calculations at the very end, which includes the 3 fiber to the X scenarios, as we said before. So for fiber to the home, you see the whole area has been calculated, and if you zoom in for a relatively dense area, you see where cables are routed through the colors that you see on the side of the street, and how they are connecting all the homes in the area. For the fiber to 5G, we can calculate the fiber routes that will interconnect all these sites to a central office. And obviously, there's a big difference if you look at the low density scenario versus a high density scenario. In this screenshot on the right with the high density, you can clearly see that the density at this stage is so high that you are virtually passing by in almost every street with a fiber network. And this shows that at this stage, convergence with a fiber to the home network that passes in those same streets is extremely high. But of course, also on the left side, most of the trenches made for these low cell densities would be shareable with the fiber to the home network. And that's what you see in the end in the converged calculation, where if you zoom in, you see that indeed most of the antennas, which are the triangles in this picture, actually integrate with the rest of the network and thus reuse ducts, cables, cabinets from the FTTH network, where ultimately also this convergence originates from. And this brings me back to the beginning of this presentation, where through these 3 calculations that we did on the for each scenario, we could calculate those 2 percentages, which are the basis of our ultimate results that we reported. And again, showing the full matrix with all the assumptions and calculations behind this, which you hopefully now have a better view on what is lying behind as assumptions and calculations. As a last part, I also want to share that apart from the reported results on the underground network, we also considered alternative scenarios. For example, with aerial cable deployments, connecting, spanning cables between poles and connecting homes with aerial drops to these poles, you obviously get a completely different way of sharing the infrastructure. If you look at these underground scenarios, and for example, taking the medium dense area, medium dense cell scenario, you could see in an aerial calculation that instead of 83% of the costs that could be avoided for 5G, you only eliminate 42. Now, the reason for that obviously being that in the 83% for the underground scenario, there is a big impact from, let's say, the dig once principle. Dig once being trenching costs are very high. If you dig only once and you put in the necessary cables for both fiber to the home and 5G, you save this trenching cost, which results in that 83. With aerial, that's much less. There, the sharing is more within the cables that you hang, that you could share fibers. Nevertheless, the 42% is still, I think, a significant number, and still rectifies the importance of convergence even in those scenarios. And at the bottom, you also see where we played around with low fiber counts instead of high fiber counts per cell, resulting in an increase of the percentage that can be saved, because the FTTH-5G network in that case is a smaller network, so more of it can be absorbed in the fiber to the home network. So in principle, we could create 100 scenarios playing around with assumptions on each of these cases. But we feel with these calculations, at least, we've explored a lot of the spectrum on what convergence really means. And that leaves me with one more message. That's to thank really the whole team that is behind this study. This was really an intensive exercise that took us around a year, where we had very valuable contributions from several partners within the council. And like I said before, on the 5G, I also want to give a special thanks to Cyrodiil and Professor Tomkos from the Athens University for their valuable contributions on these 5G assumptions and technologies. With that, I would like to hand back to Erzsébet for any questions that might have come in.
Thank you very much, Raf, for the presentation. And I also thank all the contributors on behalf of the FTTH Council Europe. As I said, a lot of the input has come from the Deployment and Operations Committee, which was the lead committee on this project, inputs from the Policy and Regulatory Working Group of the Council, and of course also from sister organizations. And of course you can see some names on the slide who were particularly strong contributors to the entire study. There are a couple of questions which have arisen. There is one question asking whether the small cells can be used by various operators, or do you assume that each operator has their own small cells?
Yes, a very good question. We don't necessarily take a clear standpoint there in that, except when it comes to probably determining the amount of fibers that we would foresee per small cell, because in essence you do have two business models typically. Business model of an dark fiber operator, an open access network, somebody who would deploy a fiber network that is ready for all kinds of operators to come on board for all kinds of applications, be it 5G or fiber to the home. I think the city fiber model, for example, in the UK is such an example. In that case, a fiber-rich scenario supporting multiple operators being able to deploy their 5G network from the same cell sites would certainly make sense, but obviously also imposes some big questions at the moment on regulation and collocation of those sites. And of course, if you look at a more vertically integrated operator, the choices could be different, and it could there be more a network that is just for one operator, and then also maybe with a lower fiber count because it's more of an internal service network.
Thank you. There is another question which is related to the EU costing study, and coupled with a request to send the source or the complete title of the study. We are certainly happy to circulate in the email sent to all of the attendees of the webinar a link also to this study, but perhaps what could be useful, Raf, is if you could just give a little background or a little summary of what that our first cost study was about.
Yes, yes, that's indeed possible. I think it's important if you look for information on the cost model to know that we actually created 3 studies on the cost model. I think the first one originated probably in 2012 or 13, so it's quite a long time ago. There, the objective was to estimate the cost for fiber to the home across the whole of Europe, so the 27 at that time member states of the European Union. And for that, we calculated a lot of areas, a lot of example areas that we ultimately extrapolated across the whole European areas to estimate what is the total fiber to the home costing if we would deploy for, let's say, 98% of Europe. So that was the first exercise. The second exercise was a focus on Germany. So from the first one, we have a detailed report, a written report. I think that's still downloadable from the website of the council. The second study then was to focus a bit on Germany. Again, there is a detailed report available for this calculation across Germany, where we kind of verified the EU-wide calculation on a national scale. And then more recently, I think 1.5 or 2 years ago, we had an update of the model where we added a couple of items like an extra member state at the time. I think Croatia added to the list. And at the same time, we also looked at the areas that were already fiberized to take them out, so we could also estimate the actual remaining investment needed to fiberize Europe. And also there, I think there is material available on the website of the council.
Indeed. Thank you very much. So there is another question saying that there is an understanding that this model envisions that the X-pool can be transported over GPON protocol and Ethernet. Is there an option to run CPRI on dark fiber?
I'm sorry, can you repeat that last part?
Is there any option to run CPRI on dark fiber?
CPRI?
Yes, it's not sure what that is.
I must admit I'm not 100% sure what that abbreviation means.
So perhaps that is something that we could check. Finally, I think one more question regarding basically kind of the sharing possibility. So have you considered a neutral host model for multiple mobile operators in dense urban areas?
So yes, what we look at is various scenarios where ultimately how many service providers come onto the network is not restricted, I would say. So we do consider scenarios where we believe what we are deploying is possible to be shared between multiple operators. And actually more and more you do see the trend with this fiber densification and fiber needs also in wireless, that given that the fact that often deploying one network for one operator and then this kind of similar network for another operator but separately is actually also not a very efficient way to do it. So there's actually the convergence between fiber to the home and 5G that we study, but you could also look at convergence between multiple operators, and the benefits there are clearly also huge because they are bringing fibers probably to similar points, and if they would share that infrastructure, they would have also significant overall savings. But again, this is obviously very much regulatory driven, what is possible there. And sometimes it's also the competitive market and the speed of deployment that will determine whether that really happens or not.
I would like to thank you, Raf, for the very interesting presentation. I would like to also thank all participants for listening and asking questions and participating in our webinar. Please don't forget that there will be another chance to get updates on our latest studies and papers at our next FTTH conference, which will take place in Berlin, 21st to 23rd of April in 2020, after our very successful Amsterdam conference, to which all of you are most welcome. And if you have any further questions, please do send them to us by email. Otherwise, you will receive the link to the video of this webinar, as well as the pack of slides, as well as a link to the original cost modeling study by email. With that, I would like to close the webinar. Thank you very much again. Goodbye.